Welcome friends, Igor is here, and in this video we will define the column space of a matrix and discover connections between column spaces and linear systems. In this lesson we will define what a column space of a matrix is, and we will discover that the question of membership in the column space is equivalent to the question of consistency of a certain linear system. Let's get started. One of the most commonly used results in this course is the fact that solutions to linear systems can be thought of as linear combinations of the columns of the coefficient matrix that are equal to the vector of constants. This observation motivates us to look at the set of all possible linear combinations of the columns of a matrix, and this leads to the definition of the column space of a matrix. Suppose that A is an M by N matrix, and we denote its columns by vectors A1, A2 through AN. This matrix has n columns, each of which is a column vector of size M. The column space of the matrix A is the span of all the columns of the matrix, and as such, it is a subset of Cm. To understand column spaces better, let's consider two linear systems. Notice that the two systems have the same coefficient matrix and they differ only in the vector of constants. Let's denote the common coefficient matrix in these linear systems by the matrix A. The vector of constants in the system on the left is B, and the vector of constants in the system on the right is C. Then we can use our usual notation for linear systems. So we can think of a first linear system as a linear system with A as the coefficient matrix and B as a vector of constants, and the second linear system has coefficient matrix A, same as the first one, but different vector of constants C. These two linear systems differ in that the system with B as a vector of constants is a consistent system, while the system with C as a vector of constants is inconsistent. Let's understand where this difference is coming from in the context of the column space of the coefficient matrix. To convince you that the linear system with B as the vector of constants is consistent, I am just going to reduce the augmented matrix of this system, and you see that in the reduced matrix the last column is not a pivot column, therefore the system is indeed consistent. Moreover, you see that x3 and x4 are free variables, therefore this system has infinitely many solutions. Let me construct one particular solution of this system by, say, assigning values of zeros to the free variables x3, x4. Then we can use the components of this solution vector as scalars in the linear combination of the columns of the coefficient matrix that will result in the vector of constants B. But this equation says that the vector B can be expressed as a linear combination of the columns of the matrix A. In other words, it is one of the linear combinations of the columns, and therefore the vector B belongs to the span of the columns of the matrix A, which is the column space of A. So to summarize, this linear system is consistent implies that the vector of constants B belongs to the column space of the coefficient matrix. You can also check that the second linear system is inconsistent by reducing its augmented matrix. As you see in the reduced matrix, the last column is a pivot column, so the system is indeed inconsistent. What it means is that it's impossible to construct a linear combination of the columns of the coefficient matrix that will equal the vector of constants C. In turn, this is saying that the vector C is not a member of the column space of the coefficient matrix. So this observation means the following. If the linear system is inconsistent, then the vector of constants does not belong to the column space of the coefficient matrix. Let's write a formal summary to what we just discovered. Suppose we have an M by N matrix A, and B is a vector of size M. Then B is a member of the column space of A if and only if the linear system with A as the coefficient matrix and B as a vector of constants is consistent. This is if and only if statement, therefore there are two separate implications for us to establish. First, in the forward direction, we are going to suppose that the vector b belongs to the column space of the matrix A. Then, by the definition of the column space, it means that the vector b belongs to the span of the columns of A, and in turn, it means that the vector b can be expressed as a linear combination of the columns of the matrix A. But now, if you take the scalars from that linear combination, then these scalars can be used to construct a solution vector to the linear system. Therefore, the linear system is consistent. In the opposite direction, let's assume that the linear system is consistent. Then it means that there is at least one solution. But the components of this solution vector can then be used to construct a linear combination of the columns of the coefficient matrix A that is equal to the vector b. And this is exactly what it means for the vector b to be a member of the column space of the matrix A. It is also possible to define the column space of a matrix using a slightly different approach. We just proved that the question of membership in the column space of the matrix A is equivalent to the question of consistency of linear system with A as the coefficient matrix and the vector under question as a vector of constants. Recalling that a linear system is consistent if and only if it has at least one solution, we can therefore construct the chain of these three equivalences. Therefore, a vector b belongs to the column space of the matrix A if and only if you can find a vector x so that the matrix vector product, matrix A multiplied by the vector x, is equal to the vector b. This observation allows us to come up with an alternative definition of the column space. So according to this equivalence that we just established, the column space of a matrix A consists of those vectors b which have a property that they're equal to the matrix A multiplied by the vector x for some vector x. But the set of vectors b which look like matrix A times some vector x can simply be expressed as a set of all vectors of the form matrix A multiplied by the vector x, where vector x runs through all the possible choices. So you can think of the column space of a matrix A as the set of vectors which can be obtained by taking this given matrix A and multiplying this matrix by all possible vectors of size n. Now, let's make sure that we understand how to check whether a given vector belongs to the column space of a given matrix. For example, we have this matrix A of size 3 by 4, and we have the given vector v of size 3. The question is, does this vector v belong to the column space of A? We just proved that the vector v is in the column space of A if and only if the linear system with A as the coefficient matrix and v as a vector of constants is consistent. Therefore, what we do is we form the augmented matrix of this linear system. And to form this augmented matrix, we take the coefficient matrix A, and to the right of that matrix, we add one extra column, the given vector v. We then reduce this augmented matrix, and from the reduced row echelon form, we see that the last column is not a pivot column. Therefore, this linear system is consistent, and in turn, it means that the given vector v does belong to the column space of the matrix A. Let's do it again. Same matrix A, but different vector w. Does this vector belong to the column space of A? We know how to proceed. We construct a linear system with the given matrix A as the coefficient matrix and the vector under question as a vector of constants. We construct the augmented matrix of this linear system and we reduce the augmented matrix. In this case, we see that in the reduced matrix, the last column is a pivot column. This means this linear system is inconsistent, and therefore we conclude that this vector w does not belong to the column space of the matrix A. If you found this video useful, and I hope more and more people do, then please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will learn how to compute column spaces of matrices. I will see you later.